Section 1110, Taylor and Maclaurin series continued. So let's head on in here and do some more examples. So you may have seen this particular one done in a class session, but I wanted to just reiterate it on the video in case you didn't have a chance to come to that class session or watch that Zoom video yet. So if you're taking a look at this Maclaurin series, you want the Maclaurin series for this trig function, f of x equals the sine of x. What we're going to do is we're going to assume, one, that this particular function does have a power series expansion, so that we can go ahead and find its power series expansion. And then we're going to read this part, this Maclaurin series, saying that we're talking about a Maclaurin series instead of a specific Taylor series at a point, is telling me that this is centered at a equals 0. That is what a Maclaurin series by definition is. It's a specific Taylor series centered at 0. So if we want this Maclaurin series, that means we want to write the sine of x. We want to come up with the power series from n equals 0 to infinity of c sub n times, now it would be x minus 0 to the nth power. That's a little bit clunky to write, so we just write, of course, x to the n, where these coefficients by our derivation for the Taylor series, and then specific to Maclaurin at 0, is going to be the nth derivative at 0 over n factorial. So this is what we need to figure out. We got to figure out how to represent these coefficients. So let's do that. And to do that, I'm going to go ahead, I'm going to make a table just so that we can see the pattern, and I'm actually going to make this table maybe a little longer than some of the other examples so that we can really see what happens here. So let's look at 0, 1, 2, 3, 4, 5, 6, 7, and 8. Might even have to zoom out so we can get it all on one screen. And so we are going to look at the nth derivative of x and then the corresponding coefficient, which is going to be that nth derivative evaluated at 0 and divided by n factorial. Now, couple quick notes from before, but also just some conventions to remember, that the 0th derivative, when we have taken no derivatives, we are talking about the actual function, and when we say 0 factorial, that is defined as 1. Okay, so if the function itself is the sine of x, then when we take the first derivative, we get the cosine of x, the next derivative, negative sine of x, negative cosine of x, and this is why I wanted to go all the way down, because by the fourth derivative, we've cycled back to the sine of x, and so I just want to show this pattern 2 times through. So the derivative of sine is cosine, derivative of cosine is negative sine, negative cosine, and then back by the 8th derivative to the sine of x. Okay. So just so that we can fully see what's going to happen here, I wanted to go out to 8 derivatives so that we can really see what's going to happen with the pattern, and that will help us when we go to write the power series. So now when I actually evaluate these derivatives at 0, notice what happens. This first term becomes 0. The second term will become 1 over 1 factorial. The next coefficient will be 0. The next coefficient will be negative 1 over 3 factorial, then 0, then positive 1 over 5 factorial, then 0, then negative 1 over 7 factorial, and then 0. So notice what is actually happening here, that every other term is actually 0. So when we go to write this power series expansion here for the sine of x, it's going to look something like this. So the power series, when we go to write it out, so the sine of x, remember, as a power series, is going to be from n equals 0 to infinity of c sub n times x to the n. So when I go and I write that out, remember that first term is 0. So the first coefficient is 0. And then we're going to have plus 1 over 1 factorial times x to the first plus 0, minus 1 over 3 factorial times x to the third plus 0, plus 1 over 5 factorial times x to the fifth plus 0, minus 1 over 7 factorial times x to the seventh plus 0. And we can see what the pattern is. We would keep going here. Then we'd have plus 1 over 9 factorial, x to the 9th, plus 0, and so on and so forth. So we can see what the pattern is, but it seems silly, and it is silly, to have a power series expansion here where half of the terms are 0. So what we want to do is we just want to reorganize this and write it in such a way that maybe we could think of it as a reindex. I'll change the index so that we'll see it really clearly. We can think of it as a reindex or a reorganization where we don't want to add up a bunch of 0 terms. That is a little bit silly to add up an infinite number of zeros. So what we can do here instead is we can say that the sign of x is actually equal to the power series from, let's say, k equals, let's go ahead and start at 0. So we can start at 0. We can start at 0 to infinity. And notice here that we have a switch, so we have -1, right? So get rid of all these 0 terms and focus in on instead the terms that are not the non-zero terms. Focus in on those non-zero terms. Notice the pattern here that we have a switch. So we've got a switch, -1 to the k. Then we have x. Then we have x raised to an odd power. So quick note up here, odd. When we're talking about odd numbers, the ways we want to express odd numbers are to use the expression 2x plus 1 or the expression 2k I meant 2k plus 1 or 2k minus 1 when we're talking about k's or n's or x's even. And if we have even numbers, then we would want to refer to those with the expression 2k would generate even numbers. So notice that the powers and the factorials, for that matter, the powers and the factorials match, and they are odd numbers. So we would write this as x to the 2k plus 1 divided by 2k plus 1 factorial. Since our k is starting at 0, that will give me my first term with x to the first and 1 factorial, and then my next term will be the next odd number, 3x to the third over 3 factorial with the appropriate switch going on. So what we've done here is we've cleaned this up a little bit. Notice the pattern, noticing that half of the terms went to 0, and rather than trying to come up with a pattern that generated half the terms being 0, we can eliminate those terms and focus in on the pattern that occurs with the non-zero terms. And so this is what the Maclaurin series expansion for the sign of x is. But now we got to figure out, well, when would this be actually equal to the sign of x? So when is this power series, on what interval and radius of convergence is this power series actually equal to sign of x? And so let's go ahead and finish off this example by finding the radius of convergence. So to find the radius of convergence, we're going to take the limit. Take L is equal to the limit as k approaches infinity of -1 to the k plus 1. We're going to have x to the 2k plus 3 when I plug in k plus 1 over 2k plus 3 factorial times 2k plus 1 factorial over -1 to the k and x to the 2k plus 1. And so we can see here lots of reduction. I notice in the factorials, on the 2 factorials, that the factorial on the bottom is going to have 2 additional factors beyond the factorial on the top, beyond the end of the factorial on the top. So I'm going to do a little bit of quick simplification here, and the negative ones obviously are going to reduce to just a -1, and then the absolute value of -1, reduce the x's, and we have just x squared times 1 over 2k plus 2 and 2k plus 3 left over from the factorial on the bottom after it reduces with the factorial on the top. And so now as we let k go to infinity, obviously this portion of the limit is going to approach 0, and we're going to end up with the absolute value of x squared times 0, which is equal to 0, which is less than 1 always. So therefore, by the ratio test, the radius of convergence is actually infinity. So not only does the sign of x have a power series expansion, but this power series expansion is true for a radius equal to infinity, or on the entire number line from -infinity to infinity. And we could show graphically that if we looked at those Taylor polynomials, as we add up those Taylor polynomials in their expanded form up above without the zeros, if we were to add those up, that we would actually find those polynomials approaching that curvature of the sine. It's phenomenal. It's fun to watch in a graphical form, and I do like to show that, and I will show that in the class sessions if you haven't already seen that. So that is what we have found now, that the actual trig function, the sine of x, can be written as a power series, an infinite polynomial with a radius of convergence of infinity. And that's pretty powerful, and we can use that. So we will add this into our bank of useful series, and we can then utilize it to do things like this. Let's do just one quick extension off of this. So let's do a quick little, we'll call it extension. Okay. Let's use the fact that we now know that the sine of x is equal to the power series from k equals 0 to infinity of -1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. And let's use that to say, I don't know, let's write or let's find the Maclaurin series for g of x equal to x squared times the sine of 3x, for instance. Okay. So if we have a known Maclaurin series, right, we know this already. We just proved this guy up here. We know that this is what the sine of x is. And I want to come up with a Maclaurin series for something similar to that, just with a product, right? We're multiplying by x squared, and we've substituted a 3x in for x. Well, let's use our known series. So we could just say, well, then it must be the case that g of x would be equal to x squared times the power series from k equals 0 to infinity of -1 to the k, substitute the 3k in there, 3k to the 2k plus 1 over 2k plus 1 factorial, and continue to simplify that out. And this is going to be true. Remember, that had a radius of infinity. So making these substitutions in that product is still going to continue to have a radius of infinity. And so then we could come in here and just say this is x squared times integral from k equals 0 to infinity of -1 to the k, 3 to the 2k plus 1, x to the 2k plus 1 over 2k plus 1 factorial, and then we could bring in this x squared and increase the power on each of those terms with x by 2. So k equals 0 to infinity of -1 to the k, 3 to the 2k plus 1, x to the 2k plus 3 over the factorial 2k plus 1. And that is what our g of x is equal to. So once we have a known series, we can work with it. Here we worked with it. We just did a little bit of algebraic manipulation. We did a substitution and a multiplication by x squared. But we could even integrate. We could, at this point, we could integrate if we wanted to. We could integrate, we could differentiate, we could take limits. We can do all sorts of things now that we know this, this power series and its associated radius of convergence, which is actually infinity. So we can definitely utilize this sine of x. So we're going to put this sine of x into our bank of useful power series, and as an exercise I'm going to have you as the students, I'm going to go ahead and have you work through the derivation for what is the Maclaurin series for the cosine of x. It's very similar work to go through that. But before we finish out this video, I would like to add in a third example, and so let's take a look at, I actually wrote it already, I was going to rewrite it, but I had it right here. So let's look at a third example, and this time let's find the Taylor series for g of x equals the natural log of x about x equals 5. Okay, so we are going to assume that this function has a power series expansion, that the remainders of the Taylor polynomials go to 0, which we can do, and we can say that if that is true, then g of x equal to the natural log of x. Now this time we're looking at a Taylor series and we're centered at 5. So that means that g of x, which is equal to the natural log of x, is going to be equal to some power series from n equals 0 to infinity of c sub n times x minus 5 to the nth, where our c sub n's are going to be equal to the nth derivative of that function, sorry, it's actually g, not f, where g, the nth derivative of g evaluated at 5 over n factorial. So that's the key. We got to figure out how could we express those coefficients. So let's figure out and see if there is some sort of pattern that we can summarize and pull in for those coefficients for this Taylor series. So let's take some derivatives and get into it. So n, and we're going to be looking at the nth derivative. I keep wanting to write f, but we're actually talking about a function called g. So take the nth derivative of x, and then after we've figured out what those nth derivatives look like, let's look at what c sub n would be, which is going to be the nth derivative actually evaluated at the point 5 divided by n factorial. Okay, so let's go ahead and take a look at that. So if we're doing that, let's do it. How many are we going to need? Possibly 4-ish. We'll see if we need more as we go. So remember, the 0th derivative is itself the function. So that's just the natural log of x. And of course, then that would be the natural log of 5 divided by 0 factorial. But 0 factorial is actually 1. So that's just going to be the natural log of 5. Okay. Now, when we take the derivative of the natural log of x, we get 1 over x. And let's work through the derivatives first, and then we'll plug in those. We'll plug in 5 and divide by the factorials as we go. So we get 1 over x. Then when we take the second derivative, we're actually going to get negative 1 over x squared. And when we take the third derivative, we're going to get a positive 1, because now we take another, we're going to multiply by negative 2. So we have a positive 1 times 2 over x to the third. And when we get to the fourth derivative, we're actually going to have a negative 1 times 2 times 3. And notice I'm not simplifying, and I don't want to simplify, because the whole point of looking at this table and taking these repeated derivatives is to get a sense as to what the pattern is here. And I hope that you can sort of notice this is a bit of an anomaly. This guy does not fit the rest of the pattern, but that's okay. So if you have a finite number of terms that don't fit the pattern, doesn't, I guess, let's say, doesn't fit the pattern, that's okay. We can always pull off a finite number of terms out of an infinite sum. So let's not worry about that first term not fitting the pattern. Let's look for the pattern starting with 1. And notice what you have here. You have a switch. So there's a switch that occurs. So if I go ... and I try to think about how could I write the nth derivative, right? If I get to the nth term before I get to Cn, if I just get to the nth term, the nth derivative is going to have a switch on it. So it's going to be negative 1. And the switch is actually going to be to the n minus 1 here. So to the n minus 1, because at 1 we have a positive, and at 2 we have a negative. So it's going to be to the n minus 1. Notice that there's a factorial arriving in the numerator. So at first we've got, you could think of this as 0 factorial, 1 factorial, 2 factorial, 3 factorial. Remember, 0 factorial is defined to be 1. And so we definitely have a factorial, and the factorial is 1 less than whatever the value, whichever term we were on. We were on the first term, second term, third term. So we can write that as n minus 1 factorial. And then, of course, in the bottom, we have x to the nth. So we have generated a pattern for the nth derivative. And this is true, this pattern is true when n is greater than or equal to 1. So we'll address that when we get over to the coefficients. And so notice what we could do here. We could actually plug these in here. And notice if we plug these in, we would have 1 over 5 times 1 factorial. We would have negative 1 over 5 squared times 2 factorial, we would have 1 times 2 over 5 cubed times 3 factorial, on and on we go. What we're going to end up having here is negative 1 to the n minus 1 times n minus 1 factorial, plugging in 5 to the nth times n factorial. So what we have done right here is we've actually found the coefficient. The coefficients c sub n are equal to negative 1 to the n minus 1 times n minus 1 factorial over 5 to the n times n factorial when, now we do have to be specific because remember that first term did not work, so when n is greater than or equal to 1. And that actually reduces. We could have reduced it in the table, but let's reduce it now. So notice right here that these 2 factorials, n minus 1 factorial and n factorial, obviously all the terms are going to cancel between those 2 factorials, except for the single factor in the denominator that goes beyond, which is n. So this is going to be equal to negative 1 to the n minus 1 over n, is all that's left in the bottom of that factorial, times 5 to the nth. And that is what our coefficients look like. So we've come up with a way to write our power series, except for the fact that we've got this guy that doesn't fit the pattern, and that's okay. We can just write that as its own term at the beginning of the power series. So g of x, which is equal to the natural log of x, centered, natural log of x, getting ahead of myself with my words, centered at x equals 5, is equal to, well, the first term. When n equals 0, we are not able to write that in the same pattern. So when n equals 0, the first term is actually just going to be natural log of 5 times x to the 0, which is 1, plus the power series where we just generated the coefficients from n equals 1 to infinity of negative 1 to the n minus 1 over n times 5 to the nth times x minus 5 to the nth power. And that is our power series representation. We have one less piece to do, and that is to figure out when, right? When can I use this equality, right? So that little star right there, when can I actually do that? So that star is, we got to find that radius of convergence. So now the last piece to do here, radius of convergence. So on what values of x can we actually use this equality that the natural log of x is actually equal to? When does this power series converge to the actual function natural log of x? And so let's go ahead and do that with a ratio test. So the limit as n goes to infinity of the absolute value of negative 1 to the n, x minus 5 to the n plus 1 over n plus 1 times 5 to the n plus 1 times n times 5 to the nth over negative 1 to the n minus 1 and x minus 5 to the nth. Let's get in there and let's actually take that limit. Before we can take the limit though, let's go ahead and do the reduction. So we're going to have x minus 5. We're going to have a single 5, and in absolute value it stays 5. So we're going to have just a single 5 when we reduce, and then we're going to be multiplying by n over n plus 1. If I multiply top and bottom of that by 1 over n, this will become the limit as n goes to infinity of x minus 5 over 5 times 1 over 1 plus 1 over n, which is equal to x minus 5 over 5 times 1, but I will leave it like that. And we know that this will converge by the ratio test. Says that this limit, when this limit is less than 1, we will have convergence. Converges when this is less than 1. So what that means is that the absolute value of x minus 5 has to be less than 5. And that tells me that my radius of convergence is equal to 5. So we can write this natural log of x centered at x equals 5 for a radius of convergence of 5, meaning we can go to the left or the right from where we're centered at, which is at 5. So we can go between 0 and 10 and have absolute convergence of this function, natural log of x, to this power series. Okay. So there is another set of examples using Maclaurin and Taylor series, using the expansions and developing the series, the power series representations of functions around certain points.